Hey everybody, welcome back to Complex Analysis. In our last lecture, we derived this result. If we take a complex number in polar form and raise it to the nth power, what we get is essentially the modulus r raised to the nth power times cosine and I sine to the n theta. So when we take a complex number, z, raise it to the nth power, the magnitude gets raised to the nth power, and the angle associated with that complex number gets multiplied by n. And we probably wondered, well, is this result restricted just to whole number exponents? Can we do something similar, let's say taking a square root or a cube root? And the answer is yes. Here, we're taking the nth root of the complex number z, and oh my goodness, I'm starting off being a wellspring of misinformation already. What we get is the modulus to the 1 over n power, and the angle associated with z is divided by n. This actually holds true. But there's more. Think about it. How many roots do we usually associate with a real number? How many square roots do we usually associate with a positive real number? 2, right? In general, a real or a complex number has n nth roots. And I'll tell you why. This thing here, the variable of our polynomial is beta. So this is a polynomial of nth degree, and we expect it to have n roots. So there are n values of beta that will give us a solution to this equation. This is just one of those values. It turns out that there are n distinct nth roots of a non-zero complex number. And we're going to list them all right now. This formula gives us all of the nth roots, all n of the nth roots. And, well, actually it doesn't. No. I is the square root of -1. K. There we go. Now this gives us all of the nth roots of z. Note, if k is equal to 0, then 2k pi is just 0, and we have theta over n, as we do up here. But as we let k range through the values from 0, 1, 2, all the way to n minus 1, this generates all of the nth roots of a complex number. So, yeah, let's try a few, okay? Let's do a couple of examples. There's our r. And this is strictly a real number. It has no imaginary part. So in the xy plane, this is a point on the x-axis, a distance of 1 unit from the origin. So the angle is 0. So r equals 1, theta equals 0. What about the square root of 1? That's going to be equal to the nth root of r, cosine of theta. Oops, I didn't write that correctly. Cosine of theta plus 2k pi over n, that's 2, plus I sine theta plus 2k pi over n for k equals 0 and 1. Okay, the real square root of 1 is just 1. Let me back up a second. For k equals 0, we get z to the 1/2 equals 1. K is 0, so this is just 0 over 2, which is 0. And I sine of 0 cosine of 0 is 1, sine of 0 is 0, so this is just 1 times 1. We get square root of 1 is 1. But there's another root. Okay, we have r to the 1/2, or 1 to the 1/2, 1. Cosine of 0, this time k is 1. So we get 0 plus 2 pi over 2, or just, well, that's pi. And we get I sine 0 plus 2 pi over 2. Okay, sine of pi, 0. Cosine of pi, -1. So we get 1 times -1 is -1. So in this example, our formula correctly gives us that the square roots of z equal 1 are 1 and -1. Well, let's do something a little less trivial. Okay, here's our next example. We're going to work with the same number, z equals 1, which in polar form is z equals 1 times cosine of 0 plus I sine of 0. So here, the modulus is 1, and the angle theta is 0. Instead of computing the square roots of z equal 1, this time we're going to compute the cube roots of z equal 1. When we computed the square roots of z equal 1, there were 2 square roots. Now that we're computing the cube roots of z equal 1, think about it. Whenever we solve for the cube root of a real number, whether it's positive or negative, how many results are we accustomed to getting? Like, let's say the cube root of 8. Well, it's 2. Or the cube root of 27. Well, it's 3. Or maybe the cube root of -8. Well, that's -2. Or the cube root of -27. That's -3. When we compute the cube root of a real number, we're accustomed to looking for one value. That's because we're only looking for real roots, real cube roots. But a complex number has, a non-zero complex number has 3 roots, but only one of them is real. And we're going to find all 3 here. According to our formula, we want the cube root of the modulus. So that's 1 to the 1/3 times the cosine of theta, which is 0, plus 2k pi over n, that's 3, plus I times the sine of theta, which is 0, plus 2k pi over n, which is 3, and k can be 0, 1, or 2, which is n minus 1 in this case. Okay, k equals 0. We get the real cube root of 1, which is just 1, times the cosine. Well, let's see, if k is 0, then 2k pi is 0, so we just get cosine of 0, plus I sine of 0. Sine of 0 is 0. Cosine of 0 is 1. So we just get 1. When k is 0, we generate the cube root of 1, which is 1. Now, let's try k equal 1. And again, we get our modulus 1 to the 1/3 power, 1. Cosine to the 0 plus 2 times 1 times pi, that's 2 pi. Oh my goodness. I think we need a cosine in there somewhere. Okay, cosine of 0 plus 2 times 1 times pi, that's 2 pi over 3. Plus I sine 2 pi over 3. Okay, cosine of 2 pi over 3. Let's see, that's going to be, well, tell you what, let's leave it in this form. Let's leave it in this form. I don't know why I was thinking that I wanted to put it in some other form. Polar form is good. Let k equal 2. So we have our modulus 1 to the 1/3 times cosine of 0 plus 2 times k, which is 2, times pi. So that's 4 pi over 3. Okay. So we did the square root of 1, both square roots of 1. We did the cube roots of 1. Maybe we should look at these things as they appear in the xy plane. Okay, here we've plotted the square roots of 1. So this is cosine of 0 plus I sine of 0. This is cosine of pi plus I sine of pi. Over here we have the cube roots of 1. Cosine of 0 plus I sine of 0. Cosine of 2 pi over 3 plus I sine of 2 pi over 3. Cosine of 4 pi over 3 plus I sine of 4 pi over 3. This picture may not suggest too much, but this picture might. Just look at where those points are. Do you see anything? As far as angles go, what's the distance from this point to that point? Well, we're going from an angle of 0 to an angle of 2 pi over 3. And here, going from this point to this point, we're going a distance from 2 pi over 3 to 4 pi over 3. So 2 pi over 3 from here to here, 2 pi over 3 from here to here. And let's see, this is the angle 0, but it's also the angle 2 pi. So if we go from here to here, we're going from 4 pi over 3 to 2 pi, but 2 pi is also 6 pi over 3, isn't it? So we're going 2 pi over 3 from here to here, 4 pi over 3 to 6 pi over 3, or 2 pi. Do you see it yet? Let me draw some lines. Well, let's see. These 3 points are equally spaced on the perimeter of the circle. See, if I were to erase that line, and that line, and that line, yep. Essentially, we've divided the circle into 3 equal parts. These 3 points are equally spaced on the perimeter of the circle. Now, in the case with the square root, it was a bit harder to see. But yeah, the 2 square roots of 1 are equally spaced on the circle. They're half a circle away from one another. So what do you think the case would be if we computed the 4th roots of 1? You think they'd be equally spaced around the circle? Well, the answer is yes. Okay, z equals 1. And using our formula, these are all the 4th roots of z. Cosine 0, I sine of 0. Cosine of 0 plus 2 pi over 4 plus I sine 2 pi over 4. Cosine of 0 plus 2 pi over 4 plus I sine 0 plus 2 pi over 4. And cosine of 0 plus 3 pi, now let's see, what would that be? Well, anyway, 3 pi over 2, 3 pi over 2. These are the 4th roots of 1, and yes, they are equally spaced around the circle. So let's see. We know what 1 nth root of 1 is, right? 1 is an nth root of 1 for any value of n. 1 is a 20th root of 1. 1 is a 15th root of 1. 1 is a 43rd root of 1. We know that the nth root of 1, no matter what n is, n being 1, 2, 3, 4, 5, 6, 7, 8, we know that the nth root of 1 for any positive whole number n, one of them is going to be right here. And all of the others are going to be equally spaced around the circle. Which means, let's see, from here all the way around the circle and back, that's 2 pi. All of the nth roots are going to be equally spaced. So just take 2 pi and divide it by n. And we go a distance of 2 pi over n, there's our first nth root. Go a distance of 2 pi over n again, that's our second nth root, and so forth. I always liked this result. The nth roots of 1 are spaced evenly around the unit circle. And I guess we can actually do even a little bit better than that. Let's see. Let's see what we can do. Well, let's see. One consequence of this result is that if z is a positive real number, then z is always going to have at least one real nth root. we can take the nth root of a positive number and get a positive number. So here's the nth root of z. And this is on the circle of radius nth root of r, where r is the modulus. Here's one of the nth roots. Well, all of the nth roots are going to be equally spaced on this circle of radius r. So let's say we want the sixth root of z, for example. Well, let's see. So let's see. 1, 2, 3, 4. Let's see, here's another one, right? Okay. So here's the sixth roots. I could have done better spacing those. But yeah, essentially, they're going to appear equally spaced around the circle. And this is going to be a circle of radius r. So if z is a positive whole number, then all of the nth roots are going to be equally spaced around the circle. And we know what one of the roots is. It's right here where the real part of z is 1 and the imaginary part is 0. Or in this case, real part is r to the 1 over n. Now suppose z is not a positive number. It makes things a little bit more challenging. In order to plot the roots of z on the unit circle, we have to find that first point. And then after we find that first point, we work our way around the circle in increments of 2 pi over n. And we'll have all n roots plotted on the circle. So now maybe this is something else that we should say in general. Okay, some more about nth roots of complex numbers. The nth root of 1, a lot of books call this the nth root of unity, and I think ours does too. But it's the nth root of 1, are equally spaced on the circumference of the unit circle. And 1 is going to be one of those nth roots. All of the other n-1 roots are going to be equally spaced on the circumference of the unit circle. The nth roots of z equal r, where r is a real number, are equally spaced on the circumference of the circle of radius nth root of r, centered at the origin. And one point will be the point xy equals nth root of r. So this will be a point on the x-axis with x-coordinate nth root of r. And now in general, the nth roots of any complex number, z equals r cosine of theta I sine theta, are equally spaced on the circumference of the circle of radius nth root of r, centered at the origin. The nth roots of any complex number are equally spaced on the circumference of this circle of radius r to the 1 over n, centered at the origin. The catch is it may be that none of those values are on the positive x-axis. In other words, none of these values may correspond to theta equals 0. That's only going to happen if z is a positive real number. But if z is any complex number, all of the nth roots will be equally spaced on this circle of radius nth root of r, centered at the origin. And if z happens to be a positive real number, then one of those roots is going to be a point on the positive x-axis. And we can work our way around the circle in increments of 2 pi over n to get all the other points.